the issue with the sound quality? A little bit of Tom. Okay. Alright, let me see here. And this is that. A little bit of kissing, yeah. Yeah, and check, check. Oh, that's what I'm looking for. Let's try that. Check, check. That's a lot louder.
It's louder?
Yep.
Oh, you mean the...
Yeah. On the...
use the Mon one.
Check, check. Check, check. Check, check. All right. Let's see. Yeah, it is. Whoop. Go ahead and take a look at it. I think it's all right on that. Whoop. Excuse me. As I say, excuse me to the cord too. All right. Yeah. It's nice that we finally got this running. Hey, how you guys doing? All right. Check, check. Oh yeah, the speakers are actually working. Hey! Getting into the big time here. We're almost having real equipment. Hey, I know you. How's it going? Good. All right. Hayden, do we have streaming to YouTube yet or no? Okay. But you've started it? Okay. I will go look. Okay, and you've got the Institute for Astronomy logo up? Fun of being the audio, video tech, and the presenter. Well, I'm going to turn it down just a bit. All right. Hopefully that way we won't crack if I go too loud. No. I'll just have to talk quiet, which is a challenge for me. All right. Let's see here. That's the master. Do we still have pretty good sound there? Okay. And you are live streaming or no? Okay. Oh, yeah. There we go. Just wandering around. It's a bit of a delay. Got 1 more minute. All right. You good? Everyone else good? Excuse me. Oh, we'll want to leave that one on. Frog in my throat. There we go. All right, we're all good? Well, welcome everyone to the Maui Institute for Astronomy. I'm Dr. J.D. Armstrong, the Maui Technology Education and Outreach Specialist. And we wanted to, every now and then I'll hijack these talks for my own purposes, and this is one of those times. And so this is a little bit of a take on a talk I gave several years ago, but I figure everyone has forgotten about it. So I thought I would take the same information and put it in a new wrapper and see if anyone noticed. So the topic of the talk tonight is what makes the sun shine, and this is supposed to be an introduction to solar physics, but we don't want to be boring, right? Okay, so I'm going to try to make it a little bit fun. And so what we're going to do is I'm going to figure out why the presentation clicker isn't working. Oh, the battery's dead, that's why. So, we're going to do an escape room adventure. All right? So we're going to try and escape from the sun. Everyone ready for this? How many of you have actually done an escape room? Was it fun? Okay, great. So escape from the sun. So the idea of this escape room is that we're going to help the photon family escape from the house of the sun. And the names of the photon family are Phil, Phyllis, Phoebe, Phoenix, Phineas, and Doris. Thank you. Somebody at least noticed. All right. Some things that are going to help you. These are clues that you're going to need for this escape room. Is that the sun is about 4.6 billion years old. It'll live for about 10 billion years old as a main sequence star. It's kind of like what it is now. The sun's made of 73% hydrogen, 25% helium, and then a little bit of what we call metals. Okay? Now the radius of the sun is 6.96 times 10 to the 5th kilometers, and the mass of the sun is About 2 times 10 to the 30th kilograms. And we've got a solar physicist in back that you'll check my numbers, right? Okay. Both of us look at each other going, I don't remember the numbers off the top of my head. Let me look that up. We'll get out our cell phones later and check it. Okay? So the question is, what do those numbers mean? So the radius of the sun it's the distance from the center of the sun to the surface. Okay? And that's so 6.96 times 10 to the 5th, so nearly 700,000 kilometers. Okay? 2 times 10 to the 30th kilograms. That's a 2 with 30 zeros behind it. That's how many kilograms it weighs. Pretty big? Pretty impressive? All right. So the sun is big, let's face it. And the sun radiates 384.6 yodawatts of energy. I was not familiar with yodawatts until I was preparing this talk the first time. Anyway, really big number of energy. We'll take that number and we'll use that in a minute. All right? Okay. So we start at the center of the sun, and the center of the sun is called the core of the sun. And we're to help the photon family escape the sun, and if we fail, what happens to the Earth? If the light can't get out of the sun, what happens to us here? Gets really cold. End of life. It's, you know, am I right that escape rooms always have a doomsday scenario if you fail? I don't know. Well, we're not going to fail, right? We're too good a team. All right, so good luck on this. So the core of the sun, this is the core of the sun here. It's the center, and it extends from about 25% of the radius, from the center to 25% of the radius of the sun. And it's about a third of the mass of the sun is compressed, packed into this one small part of the sun. And it's where energy is generated. About 99% of the energy is generated in the core. All right? Am I in a good place for light? Okay, good. So, here we go. So wait, it's dark. So where are the photons? The first thing we need to figure out is, where are the photons? Where are our photon family? That's not what I wanted to do. Sure, laugh at me. Gee. Put that right there. Okay. Photons are energy, and energy is created in the core of the sun. Maybe we burned something, right? It was originally thought that maybe the sun was like a big fire. Okay? So, the sun is 4.6 billion years old. It generates 384.6 yodawatts of energy. And the mass of the sun is 2 times 10 to the 30th kilograms. We already had that. Okay? So, 10 billion years is 1.45 times 10 to the 17 seconds. We can calculate how many seconds there are in a year and multiply that by 10 billion. Okay. The sun radiates this, huge amount of solar energy. All right. So what we're going to do is we're going to multiply how long the sun's going to live and by the amount of energy it puts out per second. And that's going to tell us how much total energy the sun's going to put out in its lifetime. 15 million Kelvin. The pressure is 3.84 trillion pounds per square inch. Yeah. You thought your tires were overinflated, right? Okay. So what do we need to do? We need to set the temperature on the thermostat up to 15 million Kelvin. All right. And so what we're going to watch for, hopefully, 4 hydrogen atoms are going to be fused into 1 helium atom. There are a few things that have to be conserved. Okay? Electric charge has to be conserved. So in other words, if you've got a positive charge, have you guys, everyone's seen static electricity? Maybe you shuffled your feet across the floor and zapped, your sister or brother, and yeah, you've done that, haven't you? Okay, so that's electric charge. But you can't build up electric charge through this. You can only, electric charge is something that's conserved. You can move it from one place to another, and that's how you build up a charge to zap somebody, is you're leaving some electrons on the floor, or you're taking some electrons from the floor. Okay? But the electrons, the charge, can't be created, can't be destroyed. Baryons are the heavy particles, the nuclear particles. So we start with 4 centers of a hydrogen atom. We have to have 4 particles that are like that when we end. We also need to conserve leptons. These are light particles, like electrons are leptons. There are some other types of particles that are leptons as well. The other thing we have to conserve is, well, we think that energy, you probably have heard that energy has to be conserved, but it's really energy mass. Okay, you can convert mass into energy, or maybe you could convert it, or you could convert energy into mass. But there's sort of a total quantity there that needs to be conserved. Following? So let's see if our fusion in the sun can work. So what we're going to do is we're going to take these 4 protons and we're going to squish them down, and we're going to get 2 neutrons in the center. So 2 of these protons turn into neutrons. Okay? And then the other 2 just go in there. The reason that you need the 2 neutrons is the protons have the same charge, so they push apart. They actually try to push each other apart. But there's an even stronger force than electric force called the nuclear strong force that holds this together. And you need a couple extra neutrons in there to provide enough nuclear force to hold it all together. You also produce 2 electron neutrinos and 6 photons. Okay? Neutrinos are a little bit like cockroaches. They have no charge. The electron neutrinos are anti-leptons. They're minus, or let me see, they're leptons. Okay, they're light particles. And the reason they're like cockroaches is they go through just about anything. It's very hard to get anything to interact with them. And then the photons, there's no mass to them, but they have energy. And photons are particles of light. Okay, they're little pieces of light. So let's see if everything was conserved here. Okay, so we went from protons, from 4 hydrogen to a helium. So before, we had these 4 hydrogen atoms, 1, 2, 3, 4. After we've got this helium atom, and 26.73 mega electron volts of energy that are the photon family. And these 2 neutrinos. Okay? So, electric charge, this has plus 1 electric charge. The electron has minus 1. So, what is plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. 0, right. He's got it. Okay, these have 0 charge. Those are our neutrons, right? So what is 0 plus 0 plus 1 plus 1 minus 1 minus 1? 0 again. So electric charge is conserved, right? Before it was 0, afterwards it's 0. Oh, and I forgot the neutrinos, which are 0 electric charge also. Okay, so we can add 2 more zeros and still be 0, right? Okay, good. So leptons. Before, we have 1, 2, 3, 4 for the electrons. Afterwards, we've got 2 electrons and 2 neutrinos. So how many leptons were there before? 1, 4. 4 leptons beforehand. How many after? The neutrinos are leptons. This is great. We got this young guy doing nuclear physics here. You're ready to go to college, right? So you've got, so did we conserve leptons? How many did we have first? So we had 4 to begin with, and we have 4 afterwards. So we conserved leptons, but we have this annoying amount of energy that we created. Where did that come from? Okay. So hopefully this animation will look good on the screen, on the big screen. Let's look and see whether or not mass was conserved. So I'm going to take the 4 hydrogen atoms. I'm going to put them in a scale. That looked better on the when I was on the screen upstairs. And I'm going to take the helium atom. I'm going to put and the 2 neutrinos, and I'm going to put those in the scale. Okay. Neutrinos are actually pretty light. They're very, very light. But they do have mass. Okay? And so if we were to weigh these 2 particles, what we had before, and weigh what we have after, what we had before actually weighs more than what we have afterwards. Okay? So can anyone think of where this energy came from? So what are we missing here? We're missing some mass, right? Okay. And the mass turned into energy. Okay, so we've got 26.73 mega electron volts of energy that was converted from mass. So literally we're taking the weight of stuff and decreasing it and getting energy by doing that. Okay? But we can't just turn all the mass into energy, otherwise we wouldn't be conserving our lepton number and our other conserved quantities. Okay? So we have nuclear fusion. Okay? So we've got, so we can do this. We can convert mass into energy. And so if we do this at the center of the sun, do we have this huge explosion going on? I mean, the sun's a giant hydrogen bomb, isn't it? Well, the power of the sun is sort of this big number of the yodawatts of energy. And the mass of the core is another big number here. All right? So, in the core of the sun, if we divide how much mass we have, or if we divide the power generated, how fast we're generating energy, by the mass. So for each kilogram of mass in the core of the sun, how much energy are we generating? Is that a lot or a little? A lot, a lot. Anyone else? Yeah? Yeah. Okay. It is this little tiny amount of watts per kilogram. Okay, now this is something outside of the realm of what we think of. We don't typically think about these numbers. So let me give you a comparison to a person. About 500 times more energy is generated by a human being, a person, than by the sun per kilogram. So the sun generates energy as though more like a compost pile. You know how a compost pile heats up? It's more comparable to the energy generation in a compost pile. But it's such a big compost pile that all of that energy adds up. Okay? So did you know that you were more energetic than the sun? You do now, right? Okay. So here's the sun. So we get this blink. And you can see the neutrinos running off there and our photons. So it's not some big explosion. It's just these little plinks. And we found our photon family. So this is the... Good. I'm glad somebody gets some amusement out of these. Yeah, I'm not sure which one's Phil. Okay. Well, yeah, we found them. We can free them from the sun now. Okay. So next thing we need to do is that the photons need to go through the radiative zone. Okay, and the radiative zone starts where the fusion of the sun ends. 99% of the fusion happens in the core of the sun. And then up here, this is the radiative zone. And it's just basically a lot of plasma, which is hydrogen with the electrons separated, or helium with the electrons separated. It's a big layer of plasma. And energy is transported by radiation. So the motion of light is how the energy gets out of the sun. Well, we've got photons, and so this should be easy, right? Okay? So the photons must travel through the radiative zone to make it out of the sun. Ready? So here's our radiative zone. Well, there goes the neutrinos. This should be easy, right? All right, here we'll have Phil the photon go first. You ready? Okay. What happens is the light bounces around. It goes from nucleus to nucleus and from electron to electron, and it bounces quite a bit. In total, for the light to get out of the sun, it takes something like 1 million years. So this is a very long escape room. To the surface, yeah. 1 million years. And this is where a lot of the time is spent, is at the radiative zone. So as this photon, it's traveling at the speed of light because it's light. Okay? It bounces around. And it gives energy to the plasma, or gets energy from the plasma until it kind of comes into an equilibrium. And then it just keeps on bouncing around. And photons are absorbed and created. But eventually, this light kind of diffuses out towards the top. Okay? All right. Did I put this slide in twice? I think I did. Okay, let's watch it again. All right. Okay, so the next layer of the sun is the convection zone. Radiative zone ends, and it extends from about 71% of the solar radius up to the surface of the sun. Okay? And at this point, light or energy is actually transported by convection. So the energy is picked up by the plasma at the base of the convection zone, the top of the radiative zone, and it heats up the plasma and it floats to the top. So let's look at that. Okay. No one's going to ooh and ah over this. Okay, fine. I went to a lot of, Yeah. Okay. Thank you. Thank you. So here's our photon. And what's happening is it's actually driven from the top of the convection zone. Okay? Here's the radiative zone. This is the area where it bounces around. It's not really red. It's actually probably pretty blue if you were able to look at it. But I'm using red because to our minds that reminds us it's hot. Okay? It's hotter than red, and blue is actually hotter than red. Okay? So you have cold downflow. It's driven by downflow from the surface of the sun. And these downflows can actually start going faster than the speed of sound. So it gets down to the bottom of the convection zone, and then the radiative zone, which is hotter, heats that up. Okay? And then when it heats up, it expands, so it's lighter and it floats up. So you've got, think of little parcels of plasma cooling and contracting and sinking down, getting to the bottom of the convection zone, heating up, expanding, and floating back up again. All right? And that is how our energy gets through the convection zone. But it's actually faster. It takes less time to go from here to here. There have been some estimates that it's only a few months for the energy to get through the radiative zone. Depends on who you ask, I think, on that one. If you ask Jeff, he's told me a few months. Okay? So what's going to be on top of the convection zone? The surface. Okay, what is the surface of the sun? When you look at the sun, you see the surface, right? Except for you don't look without protecting your eyes. Okay? So the surface is the last place where the photons interact with the plasma. Okay? In other words, that's how far down into the sun we see. That's how we define the surface of the sun. Make sense? And it's really a gas. And so there's not like some hard surface that you put your hand against and you can feel. It's just kind of continuous. It's just, it's denser down here than up here. And at some point, that's as far in as you can see. And what's happening is, since that is the last place the photons interact with the gas, the photons are just kind of released at that point, and they can go off into space. And as the photons are released, that's how the plasma cools off, because its energy is leaving the plasma. Yep. And that's supposed to be an animated GIF, but it's not running. But the idea is that you can see the bright points here, the bright regions of the sun, or the bright cells, and then in between is the dark, and the dark is actually cooler, and so it's actually sinking down. Okay, and so I would encourage you to go and watch a video of this. This is an actual image, and it was University of Alabama's. No, I don't think that this is a simulation. I think this was a high-resolution, ground-based. Yeah. Except for, remember, this dark spot on the sun is still extremely bright. It's just they've adjusted the contrast so that dark is relative. And that's actually what the sun looks like. Say that again. That's a good question. Is it a black and white image? Why would you think it's a black and white image? Okay, well, what color is the sun? Okay, so the answer is the sun is a red, orange, yellow. You brought your imagination with you, didn't you? Yeah, you brought your imagination with you, right? Okay, good. Okay. What color is this paper? It's a white piece of paper, right? Okay. I've got a blue light here. I'm shining it on the blue light on the white piece of paper. What color does it look? Looks blue. Okay, now I'm going to turn this over. Now it's green. What color does the paper look? How about with the red? So the color of light shining on this paper will make it look that color, right? And if I'm outside and I look at and put the paper in the sunlight, what color does paper look like in the sunlight? It looks white. And try this. Try this at home. Take a piece of paper outside and look at it. That's the color of the sunlight. How many, has anyone personally tried this? So sunlight is white. And so if the sunlight is white, what color is the sun? White. It's a little bit greenish yellow. There's a little tint of greenish yellow, but it's actually pretty close to white. To our eyes, it would actually look white. So is that a color image? Could be. I don't know. Being honest. It probably to make this, they might have used a hydrogen alpha filter, which is it looks at a spectral line in hydrogen, and it shows the contrast a lot better. Okay? So. Oh, the solar viewers? Mm-hmm. Okay, so the question is, if the sun is white, why is it when we look through these solar eclipse viewers, or it looks yellow through those? What color is the filter on those? Yeah, so I think that there's adding color. There's being color added by that, and it's filtering out more of the blue light than the red light, and so more red light gets through, kind of yellowish red light. Mm-hmm. Yeah, it would look white. I believe Polaris, the North Star, is kind of similar in color to the sun. So go out and look at the stars, and you'll notice some of the stars, if you really look carefully, you can see that there's definitely color in stars. Okay? But a lot of them appear fairly white. Okay? You can look at, right now, Antares, the heart of Scorpius, is up, and that's a red star. And when that's not up, you can look in Orion, and Betelgeuse is also a red star. And so you can look at those for comparison. So look at the stars and see how many of them are white and how many of them you see some real color to. And part of that's a little bit of a trick. The stars, it'll help you see the color much better. Okay. The moon. Oh yeah, the moon. It's actually, the moon is actually black. Yeah, the white light coming off the light coming off the moon is white. Okay? But the moon is surprisingly quite dark. If you go out into the parking lot and look at the weathered asphalt, that's about what the moon is. Okay? Am I boring you to tears yet? Okay. Well, I've got to talk to the youngest person in the audience, because that's where I'll really bore people. Well, let's talk. So basically, we've gotten the photons out of the sun, because the surface is the last place that's going to capture them. But as we're going out let's at least take a little bit of a look at what we're going past. So the chromosphere is like the atmosphere. This is the atmosphere of the sun. And in the chromosphere, that's where the temperature reaches the minimum. Now, okay, hot things heat up cold things, not the other way around, right? So then you go up into the corona, which is further out and has to be heated by the chromosphere, and suddenly the temperature increases. So you've got something cold heating up something hot. Does that make sense? Yeah. And solar scientists, I mean, do you have any new understanding of why that is? Okay, so the response from one of our solar physicists in the back is that if you can find the answer to why, it quite possibly is a Nobel Prize, because it's a very big question about the temperature in the corona reaches 1 to 2 million degrees. The surface of the sun is 5,777 degrees, about 6,000 degrees. So it gets very hot. Part of that, actually, we had a partial explanation for that. Some researchers here on Maui suggested that sound waves traveling up through the solar atmosphere can become shocked and can heat up the corona. But I don't think we found that there was enough energy to explain the full temperature. So it's still an open question. Okay? And then the upper levels, the very top levels of the atmosphere, it's so hot that the particles are bouncing around so fast that the ones going outward just go streaming out, and they leave the sun forever too. So it's not just the neutrinos that are leaving the sun, not just the photons, but also little bits of the upper atmosphere gets boiled off. Okay? And we call that the solar wind. Okay? This is a comet, and it's not coming through great on this. A comet is a chunk of ice, and when it's in space, the atmosphere, or when it's in space, the vacuum means you can't have liquid water. So when it gets heated up, it goes straight to steam. It becomes gas. It sublimes. And so somewhere in the middle here, there's a little chunk of ice, and it's being heated by the sun, and that forms this big cloud around the comet. Exactly, of steam. And then the solar wind, and the light too, push back the dust and gas that are in that cloud, forming a tail. Yeah. If you turn around the computer, you can look at it. See, it's a little better on that screen, isn't it? are pretty much the only thing that existed when the universe was born. The carbon, the oxygen, the iron, all of these other materials were created in stars and then ejected back out into space, where they eventually became made the Earth and us and everything else. And so your body, which is made of a lot of carbon and oxygen and things like that, all that stuff was in a star. Right on. Okay, yes, you had another question. Good. Mm-hmm. Yeah. So the question is, the core of the Earth is made of molten iron. Okay, in the center of the Earth there is molten iron, and is there the same molten iron in the sun? A little bit, many times the mass of the Earth, but compared to the amount of hydrogen and helium, it's only a little bit. And we actually even see that iron in the atmosphere of the sun, in the corona, and we use the iron to measure magnetic field lines. Not because it's magnetic, but because there are spectral line transitions there that are very useful for measuring the strength of magnetic field lines. And so there's a little bit of iron in the sun. Yes. Mm-hmm. So the question is about the solar maximums and solar minimums. When we want to look and see if the tide is going to be high or low, you can go online and you can see predictions of when there's high tide and low tide. Is there somewhere to go online to predict that'll tell you when the solar maximums are going to occur and when the solar minimums are going to occur? Not predict, no. We're still having a very difficult time predicting the solar cycle. Some people have made some progress on that. They claim to be able to predict them, and then every time that I've seen, they've always come back and said, "Well, we were close." Is that about what your experience is? Mm-hmm. 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 Yeah. I'm getting confirmation here that it's better than guesses, but not that in many cases not better than guesses. It's very difficult to predict the solar cycle, and in particular, what they're trying to predict is the strength of it, and they don't have a very good track record. Yeah. No, it's not. The frequency is not stable. It's about 11 years. Sometimes it'll be 10 years, sometimes it'll be 12 years, sometimes, hmm Yeah, and yeah, the period changes, the strength of how strong the maximum is changes. For a while they kept saying, "Oh, well, shorter ones are stronger and bigger ones are weaker." I think wasn't that it? And yeah, both of the other solar physicists are in the background, just kind of shaking their heads, going, "Yeah." Yeah, and then there's the Mondar minimum. Okay, Isaac Newton no, Galileo. So Galileo had this wonderful thing called a telescope that no one else had used. And he'd heard about sunspots. And so he went to observe sunspots. And there were no sunspots. And so he waited 11 years and there were still no sunspots. He was, for a long period, for a fairly long stretch, called the Mondar Minimum, there were no sunspots. It was a very long solar minimum. It lasted several solar cycles, several expected solar cycles. So sometimes the solar cycles just go away altogether. And yeah, it's very difficult to, we can't predict them. We think we understand them. Predicting the weather. And predicting the weather is where chaos theory came from, because they realized when they went through and did the calculations, the computer crashed at one point, or stopped running for some reason at one point, and so they took the numbers from where they'd printed out the numbers from the simulation, and they put those back in to start at that place, and they noticed that the numbers soon were not matching what had come out the previous time. And the reason was that they dropped off the little bits at the end, and those little bits at the end made a big difference. And they concluded that the difference between a calm day in New York and a rainy day in New York could be as little as the pressure caused by a butterfly's wings in a few days before. Yeah, well, there are a lot of variables, but even more, little deviations, yeah, impact a lot. So very small initial changes down the road can make very large changes. Yes. Yes. Solar wind. Can I define the term solar wind in layman's terms? It's just the upper atmosphere of the sun boiling off, streaming off. Okay? And so it is a wind. So it's particles, it's like hydrogen and helium mostly, flowing out from the sun. And it's very low density. It's much lower density than even our vacuum chamber can hit. But it's a real conceptual wind. Just, yeah. Yeah, it goes up and down. Sometimes you'll have windier days. Sometimes you'll have calmer days. But how far out do the winds go? To what's called the heliopause. So there is gas all through between the stars. There's still gas. It's very, very low density. So you have a very low density wind coming up against this low density gas, and it'll push the low density gas around, but only so far. And at that point, you know, you kind of have the end of the solar wind and the start of just the static gas. And that's what we call the heliopause. Could the wind be harnessed? Yes, it could. The idea is solar cells. So you can have a very large cell that would collect that wind and push against the sail, and also the light pushes against the sail, and you can accelerate something outside of going out from the sun. Okay? And you guys know that you can correct me if I say anything wrong, right? Yeah, the comment is that the cells are primarily light. I think that's right too. But in principle, you know, I'm just looking for a way to say, yes, we could harness it, but it's more theoretical how we would harness it. So how fast is it going? There's a fast and a slow component, and the fast is about, what, a third of the speed of light? 700 kilometers per second is the fast component, and the slow component is 300 to 400 kilometers per second. Okay. 1.6 kilometers per mile. Okay. All right. Yes, and then I'll come back. Yottawatt. Okay, what is a yottawatt? It is 10 times 10 to the 24th watts. So that's a 1 with 24 zeros behind it. Let's write that one out. So one, two, three, four, five, six. Okay, just put those over here. That's a yottawatt. Did I get that right? Okay. You and then. Mm-hmm. Mm-hmm. Okay, so the question is kind of spawned from efficiency of solar cells, and Germans are trying to get up to 54% efficiency, and they're talking about capturing the radiation from the sun. The radiation from the sun, there are two types. Okay, there's in my mind there's particle radiation, and then there's electromagnetic radiation. So the particle radiation is the protons, electrons, and alpha particles. The alpha particle is just the center of a helium atom. Just it's accelerated really fast. And that's one of the types of radiation that you get from a nuclear reactor. Typically when you have fission of nuclear material, like uranium fuses or fizzes. Fizzes? Is that what? Okay, good. We've got the chemist in here. All right. So yeah, when it splits, it'll release an alpha particle. Okay. You can also have neutrons going very fast, which is another type of radiation. You can have protons going very fast. That's a type of radiation. And you can have electrons. Electrons and alpha particles are the most common, and electrons are beta particles. So you have alphas, which are the nucleus of helium. Betas are the electrons. Okay. Then you can also have electromagnetic radiation, which is a big source of electromagnetic radiation. Light is electromagnetic radiation. The shorter the wavelength, the more each of those photons, more energy each one of those photons has. And when you get it short enough wavelength, so blue is the shortest, is towards the short end, and then after blue you get violet, which is a little shorter, ultraviolet, which is even shorter. And at ultraviolet, we start getting to the point that you can cause damage to cells. You can go shorter into X-rays, and that's even more energy per photon, and into gamma rays. So those are non-particle radiation, what I'm calling non-particle radiation. Okay? I guess maybe non-massive might be a better division. Okay? So those are the two types of radiation from the sun: is the massive radiation, particle radiation, and the electromagnetic radiation. Let's go ahead and wake this up just so we have something to look at for entertainment. And the solar cells are collecting specifically the electromagnetic radiation, the light. And probably what the Germans are trying to do is cover a larger range of wavelengths. And so it's just, typically there's only a certain range of light that you can actually use that generates electricity in the solar cells, and that's a lot of where you have losses on those. Mm-hmm. The shorter wavelengths of light, the question is that they don't travel as far. The atmosphere blocks the shorter wavelength. It tends to block the shorter wavelengths of light. It blocks almost all of the X-ray and gamma rays. UV, some of that gets through. And then by the time we get to blue, more of that's getting through, though you can actually see the sky scattering the blue light because that's why the sky is blue. And then when you get into red, it's not scattering as much. When you get into the infrared, if you get far enough into the infrared, even during the daytime, the sky is black because it doesn't scatter that light. And so the infrared can go, lots of wavelengths of infrared can actually go right through the atmosphere with no trouble. And so that's probably what you're thinking of. In the vacuum of space, light just keeps on going. It doesn't matter what color it is. Mm-hmm. Okay. Yeah.
Think how clever it is, because that's 24 hours a day, whereas solar panels are like during daylight.
Mm-hmm. So, oh yeah. So how clever it would be if we could do something that had that collected the particle radiation. Well, particle radiation doesn't make it through the atmosphere. Okay. In fact, it kind of generally doesn't make it to the atmosphere because you've got this big bubble of magnetic field around the Earth that directs it all towards the poles. And then these charged particles come into the atmosphere and make the atmosphere glow, and we call that the aurora borealis or aurora australis. Okay? So the particles actually generally don't even make it to us during the day, and then certainly they don't make it to us during the night unless there's something to curve them around to us. So, but yeah, no, but it's great to have your mind thinking like that. All right? Did you have a question? I keep seeing your hand go up and then you, and I think I saw someone over here. Okay. Is there any rock at all in the sun? Yeah. Well, there's no solid rock. Okay? Silicon, which is, rocks are made of silicon dioxide. That's a lot of what they're made of. Okay? And silicon dioxide, there's silicon and oxygen combined. So basically it's, I guess, like burned silicon. It's like silicon ash, I guess. Okay? That's what a rock is. And there's no silicon dioxide in the sun because it's so hot that the oxygen and silicon just break apart. But there is oxygen there, trace amounts, very small amounts. And there is silicon there, there's iron there, copper there. All the elements are on the sun, but it's just so hot that they're all broken apart. They're individual atoms, and the atoms, a lot of the electrons are pulled away. And so it's all plasma. It's a gas that's electrically charged. There's no solid. Is that what you were asking? Is whether there was a solid rock? Yeah. No, there's nothing solid in the sun. Am I right? Am I missing something? Nothing solid in the sun. It's just way too hot. Yep. No igneous rock. It's too hot for lava. Lava would boil on the sun. Okay? Even tungsten. Tungsten, you can heat tungsten up hotter than any other material that we know of, and it just glows. I mean, you can get it glowing hot. Even tungsten, when you put it on the sun, gas. It's a metal. It's a metal. Afterwards, if you want, I can show you a piece of tungsten that we use. Okay.
I have a question.
Yeah.
How long has the human race been seriously observing the sun? And if it's been very long, why can't we come up with some sort of guesstimate about this sort of thing? Maybe really since Galileo's time?
So the question is, how long have people been seriously observing the sun? And if it's been long enough, why can't we come up with some kind of estimates of solar flares, some kind of predictions? The Chinese astronomers have been observing since what BC? Do you guys know right off? Since before 0 BC. Okay. And what they would do is the Gobi Desert would act as a filter to kind of protect their eyes, and then near sunset they could actually see the sunspots. And the Vatican, they observed. They had a long, hundreds of years of observing the sun using basically what's called a camera obscura, a pinhole camera. So you had a little hole in the wall over here, and over here you get an image of the sun, and you can see the sunspots. The problem is they don't have measurements of the magnetic field. It's taken advanced technology to do that. They didn't have the understanding of physics that we have today, and we're still learning more physics and learning better ways to observe the sun. We just don't have the observations yet to really make those predictions.
Would there be a record of the aurora borealis coming as far south as Hawaii?
Yeah, there is a record of the aurora borealis coming as far south as Hawaii. So sort of what you're asking is, if there were other events like that, like the one where we have the aurora borealis in Hawaii, wouldn't there be a record of it? Probably, but not necessarily. That's sort of getting into archaeology, which is less my field. So, yeah. So, okay, yeah. Mm-hmm. So the question is, on an Hertzsprung-Russell diagram, where is the sun on that? And so, I just had a pen, I know. So, if you're watching at home, look up a color magnitude diagram, and okay, this side is blue. Okay, and this side is red. Okay, this is what's called the main sequence. This is the hydrogen being fused into helium, and the sun comes in somewhere in there. It's a main sequence star. Okay, and yeah, and the size of stars ranges from about 10% of the mass of the sun, I think a little less, up to about 100 times the mass of the sun. I think some people are saying a few times more even, but something like a tenth of the mass of the sun, up to 100 times. No, so this is just the question is, as we're going down the slope, it's getting older. No, actually, this is based on how big the star is. Okay? So most stars, they don't lose tremendous amounts of mass while they're on the main sequence, and stars spend about 90% of their life on the main sequence. And you guys know to correct me if I'm wrong. We've got several astronomers here, several professional astronomers here, so hopefully they will catch me if I make any mistakes. Stars typically spend 90% of their life on the main sequence. Thank you. And but when they get older, what'll happen is they'll start getting red. And typically they'll swell up into what's called a red giant stage. Okay? So for example, our sun, after most of the hydrogen in the core has been fused into helium, then there's sort of a shell around the core that is still fusing hydrogen, and the whole star swells up. Okay? And it becomes a giant, and it's, I think, something like the radius of Mercury's orbit in the first red giant stage. It's something like that. It's a guess. It's a guesstimate. Stellar evolution is not my specialty. But then when you build up enough helium in the core and the temperature gets hot enough, you can start fusing helium into carbon. And that gives off energy. But at a smaller fraction of the mass is converted into energy. So it doesn't last as long. But when the core starts fusing helium into carbon, the star shrinks back down. Okay? Then, when all the helium in the core is exhausted, you've built up a core of carbon now. Now you've got a shell of helium burning here, a shell of hydrogen here, not burning, but fusing. So a shell of helium fusing into carbon around this core of carbon, and you've got a shell of hydrogen fusing into helium around the helium fusing shell, and then you swell up into another red giant stage where it's about the surface of the sun is about to the orbital radius of the Earth. So we would be like skimming the surface of the sun. If you want to know more about this, I know of a really great resource if you'd like to see it. Okay. Las Cumbres Observatories made a project called came from the previous generation of stars. But they're all made from hydrogen and helium to begin with. But as they age, the hydrogen fuses into helium. Okay? After that, then I can no longer say that they're made of mostly just hydrogen and helium. Eventually, you're going to fuse enough helium into carbon that you have to be honest and say, yeah, it's also got carbon, and then nitrogen, and then oxygen, and all the way up to iron. Iron is as heavy as you can get and still release energy. Okay, if you go any heavier than iron, you actually have to put energy in to make it. So uranium is heavier than iron. Okay, a single atom of uranium is heavier than a single atom of iron. There are more nucleons in there, more protons and neutrons in the nucleus, and you actually have to give it energy in order to stick them all together. Yeah. What massive star will explode rather than becoming a white dwarf? I think it's about 7 times the mass of the sun. 7 or 8. Okay, so Dr. Shea is saying about 8, and we'll go with her because she's currently teaching Astronomy 110 and other classes, and that's how I learned the number. Oh, that was from your qualifying exam. So yeah, when she was getting her PhD here. 8 times larger than the sun.
And then what about a star that will become a black hole?
Black hole, I don't remember a Chandrasekhar limit. I don't remember what that. I would check it on Wikipedia if you want to know. Wikipedia tends to actually be pretty good when you stick to the hard sciences. Okay, for astronomy, it tends to be pretty good. Yeah. Broad stroke, the creation of the solar flares. Yeah. Okay. So what happens? I'm beginning to wonder if maybe one of these days for the lecture we should just have, Stump the Dummy, where everyone comes in and asks a bunch of questions. Maybe would that be a good idea for one of these talks? We'll have a panel discussion. Okay, so never mind. I'm just going to write it down here. Basically, a solar flare, they'll come from active regions. So you've got the surface of the sun, and then down at the base of the convection zone, you've got these magnetic fields that have built up. Okay? And those come up to the surface of the sun as a loop, typically. And so you'll have a sunspot here and a sunspot there. And what happens is the magnetic field stops convection, so energy can't get to the surface. And it cools off. Okay? But the magnetic field, think of the magnetic field like a rubber band. Okay? Like a whole bunch of strings of rubber bands. And it's getting pulled around by the convection cells and getting all twisted up. And so imagine twisting together these rubber bands. And eventually, you can't twist anymore, and it slips in your hand. And what happens? Right? All that energy is released. That is a coronal mass ejection. That's a solar flare and a coronal. Basically, the magnetic field just gets twisted up, and as it gets more twisted and more tangled, energy is being built up to do that. And then when it untangles spontaneously and releases a lot of energy, and it comes out as an explosion and a solar flare. Does that answer pretty well? All right. And you can go to the National Solar Observatory. Has a lot of really good things on how the sun works as well if you want more detail than I'm going into now. And a lot of really cool animations too. It's really cool. They've got some good YouTube videos. All right. Other questions? All right. Thank you. Thank you. You wanted to see some tungsten, didn't you?